All right, hey everyone. This is question 6 through 8 of the practice problems because I said I was going to do it. This is also a follow-up from the inversion video. All right, you are a Drosophila geneticist doing a chest cross to estimate recombination rates among a set of 5 loci. You cross a female who is heterozygous for recessive mutations that cause hairy body, scarlet eyes, curled wings, ebony body, rough eyes. Genotypes. To a male who has a hairy body, scarlet eyes, curled wings, and ebony body and rough eyes. The standard chromosome arrangement for these loci are H, S, T, C, Cu, E, R, O. You get the following progeny counts. There are some missing classes of recombinant progeny. You should be able to write down what recombinants are missing, which surprises you because you know that all these loci are separated by at least 6 centimorgans. One explanation may be that 2 chromosomes in the female are heterozygous for an inversion. Which inversion below is consistent with the mapping data? Parentheses denote the boundaries for the inverted region. Alright, right off the bat, how are we going to solve this problem? What are we going to do? Alright, so let's identify the parentals and the double crossovers. Alright, so we know that the parentals are the 2 highest occurring numbers, which would be 160 and 176. So these right here are going to be parentals. The double crossovers are going to be the lowest number progeny counts, and those are 10 and 14. So these right here are going to be the double crossovers, which I'm going to denote as DXO. Everything else in the middle, they're going to be single crossovers, SXO. All right, now let's write out the genotypes for all of them. We know that the parentals are wild type, and then the second parental is going to be containing all of the mutations. So let's go underneath and write out the genotypes. First one is going to be wild type, all of the loci. Second is going to contain all of the mutations. Now the mutations are hairy body, so it's going to have an H for hairy body. ST for scarlet eyes, CU for curled wings, E for ebony body, and RO for rough eyes. All right, now let's write down the genotypes for the single crossovers. We have an individual who has the hairy mutation only. Remember, these mutations are recessive, so you have to have 2 alleles that confer the recessive mutation in order for this mutation to appear. We have a hairy body and nothing else, meaning that everything else is going to be the wild type. And we only have mutations for the hairy body. So on this chromosome, we're going to have H for hairy body, and everything else is going to be wild type. I'm just H plus 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 plus. All right, on to the next one. Scarlet, curly, ebony, rough. These contain all the mutations except for the hairy mutation. So hairy is going to be plus in this case, and then all the other mutations are going to occur. ST, C, CU, E, RO. All right. Going on to this individual, we're going to have rough, and then everything else is going to be wild type. So we're going to have this right here. It's going to be RO for rough. Everything else, wild type. All right, now for this, we're going to have hairy, scarlet, curly, ebony. So this is going to have all the mutations except rough. So rough is going to be wild type, and then everything else is going to occur. We're going to have ebony, curled, scarlet eyes, and hairy body. Oh, wait. Yes, hairy body. Yes, never mind. All right, so now coming on to the double crossovers, we have hairy and rough. Everything else is going to be wild type. So we're going to have a chromosome containing hairy, rough, everything else being wild type. For the second double crossover, we're going to have scarlet, curly, and ebony. Everything else being wild type. trying to make this line straight. All right. Scarlet, curly, ebony, everything else wild type. All right, so looking at all of these different gametes and seeing what change between them. So these right here are the parentals. These right here are the double crossovers. And these right here are all the single crossovers. We see that from the parentals, in order to get this gamete out of both of these parentals, the H had to switch with the plus. So that gives us this gamete. Likewise, that also gives us this gamete right here. In order to get this gamete right here from the parentals, the RO had to switch with the plus. And so that gives this gamete, and that also gives us this gamete underneath it. In order to get the double crossovers, the H and the RO from the parentals had to switch with the pluses, and that gives us both of these gametes. So we see that there is a pattern of switching between the genes. The H and the RO are both switching. Everything else in the middle is not switching. What significance does that mean? That could mean that these genes are relatively close apart, close together, and they're not switching too frequently, or that they are located on an inversion, and they have an inverted region in which they are not able to switch, as these genes are. So for now, let's count these middle three genes as its own separate gene. And since we know that these two can flip, and we know that this right here, these three genes right here, are most likely the inverted region, that gives us the answer choice, HECUSTRO, as the correct answer choice. All right, going on to the rest of the problem. Just give me a moment. Okay. All right. All right, let's solve question 7 now. From the data above, how far is the hairy locus from the nearest inversion breakpoint? Report your answer and send to Morgan's. All right, so now what we want to do is we want to find how far the hairy locus is from the inversion. We know that this right here is the inversion, and this is the hairy locus. We want to know the distance between both of these, from H to inversion. So what that means is we want to find the recombination frequency between hairy and the inversion breakpoint. So we want to find all of the single crossovers between H and the inversion breakpoint. Here we have the inversion, and here we have H. So this right here is a crossover because in order to get from the parentals to this, you have to cross over H with this. Likewise, for the bottom one, it's also the same. So now what we're going to want to do is we're going to want to write down all of the progeny. This is looking kind of messy. Let me erase some of this. All right. So for this parental right here, we had 160 individuals, 176. Let's write it down for all of them. For the H, we had a total of 88 progeny. For the one underneath it, we had a total of 62. For these single crossovers right here, we had 66 and 54. Now for the single crossovers, they are 10 and 14. So let's calculate the recombination frequency between H and the inverted region. All right, so that would equal the progeny for, wait, is this 8? This is 58, not 88. I hate this eraser. Of course. 58. All right, so now we're going to add up all of the progeny counts for the crossover between H and that region, the inverted region. It's going to be 58 plus 66. And remember, we're going to include the double crossovers because the double crossovers are still a crossover between H and the inverted region. They should include another inversion between rough and the inverted region. But it's still a crossover between H and the inverted region, so we're going to include 10 and 14. Plus 10 plus 14 over the total progeny, which is 600. And that's going to give us, we have to plug that in a calculator. That gives us 0.246 or 24.6%. And remember, percentage is directly equal to MAP units, so that equals 24.6 MAP units. Let's just write it down as 24 MAP units. So that is the recombination rate between H, Harry, and the inversion breakpoint. So the answer would be 24. From the data table above, is there any evidence for crossover interference in this cross? All right, remember, interference means the percentage or the probability of crossovers that won't occur due to another crossover. So double crossovers are less likely to occur because of one crossover occurring. Because when one crossover occurs, you have the chromosomes and they become all tangled up, and it makes it more difficult for another crossover to occur. So it essentially means the percent of double crossovers that will not occur. All right, in order to find that, we have to find the recombination frequency for the second gene, which is RO for rough. We're going to have to do the same thing that we did for H in the inverted. It's going to be RO/inverted. For the RO crossovers, we have 54 and 10, 54 and 66. So it's going to be 66. Where is it? Sorry, I got confused between these two. This right here is the crossover between RO. Wait. Never mind. I was correct. I just wrote it wrong in this calculation. I put 58 plus 66. It should be 58 plus 62 because that's the crossover between H and plus. So this right here would have been 62. And that would have given us just 0.24, not 246. Okay. So between RO and plus, we have 66 plus 54 plus the double crossover, which is 10 and 14, over the total progeny, 600. And that gives us, if I put it in the calculator, that gives us 0.24 or 24% or 24 MAP units. All right, so now in order to find interference, we're going to use the equation I equals 1 minus expected double crossovers, or R minus I equals 1 minus observed double crossovers over the expected double crossovers. So in order to find the expected double crossovers, we take the recombination frequency for both of the genes and we multiply them by one another. So it's going to be the recombination frequency of H/inverted times the recombination frequency of RO/inverted, and that is 0.24 times 0.24. Plug that in the calculator, we get 0.0576. So that is, or 5.76% of the progeny will be double crossovers. In order to find the expected, we take the frequency for the expected double crossovers, multiply it by the progeny, which is 600 times 600. If you multiply that by 600, we get a total of 34.56 double crossovers that should be present in the progeny. Now let's plug that into the interference equation. I equals 1 minus 34. Oh, no. The observed double crossovers, we know that we had 10 and 14. So add those together, we have 24 total. So 1 minus 24 double crossovers over the expected 34 double crossovers. And that equals 0.3, which means that 30% of double crossovers did not occur. That should have occurred. Since we have this number, that tells us that interference did in fact occur. So from this set above, is there any evidence for crossover interference? Answer is yes.